Hi, it's time for another math easy solution. To discuss further into calculus with parametric curves and now go over surface area and look at part 3 of the proof series that I've been going over. And so recall in parts 1 and 2, I'll put the links in the description below, that I derived the parametric surface area formula for a surface formed by rotating a parametric curve about the x-axis. To B, and then it's this formula here, S for surface area is equal to integral from alpha to beta of 2 pi y square root times by square root dx over dt squared plus dy over dt squared, and then this is all square root then dt, where the conditions are here, where the parametric equations are x equals f of t, y equals g of t, and where t, the parameters between alpha and beta, and the derivatives f prime, g prime are continuous, and g of t is greater than 0. That's just y, so that we could rotate it around the x-axis. So basically, y is above the x-axis. Likewise, when we're rotated about the y-axis, we could do the exact same thing, and then the surface area formula is just going to be s equals 2 integral from alpha to beta of 2 pi x. That's the only thing that changes, actually. And then this is square root dx over dt squared plus dy over dt squared, and then we have dt, and in this case basically instead of having y is greater than or equal to 0, we'll have x, where x equals to f of t is greater than or equal to 0. So this is to the right of the y-axis so that we could rotate it. So for example, what we'll have if we graph this out, let's put this in the middle somewhere like this. So if you had a curve y, this is the x, and let's say this is going to be where x is positive, so we could draw something like this. Let me just see it like that, where we start off from here. Let's say this is t is equal to alpha, then at this point here we have t is equal to beta. And then if we were to rotate this about the y-axis, so this is the same thing as above, but now rotating about the y, we'll get a shape that looks like something like this. Let's try to mirror this. It goes something like that. Try to draw it a bit better. So like that, etc. Then if we draw this, and then we just rotate it across, we get a shape that looks like this. Then we have the surface area all across it, and on the other side as well. Also the general symbolic formulas as described in my earlier videos on arc length and surface area still apply for surface area for parametric curves, and that is basically recall. Should write that in black instead. So recall the formula S is equal to 2 pi y ds. So we could write them like this, and for the rotating about the y-axis, we have S is equal to integral 2 pi x ds, where, so this is the symbolic representation. I'll show you how this is easier to view. So this is the exact same thing as above here. Instead of 2 pi x, then in this giant thing we write ds, where ds is equal to square root dx over dt. So all we're doing is replacing it squared plus dy over dt squared, and then dt like that. And to get you an idea what ds is, as I've done before, what we could do is we can multiply this dt inside. So what we'll get is ds equals 2 square root. So if we square this and then put a square root so we can put that inside, we'll have a dt squared inside here, and then we have this inside dx over dt. I'm going to square both like that, plus dy over dt, and then the top squared, bottom squared, so that it's easier to see that we can just multiply this inside, and those all cancel. What we're left with is square root dx squared plus dy squared. And then we have, this is our ds. So then symbolically what this looks like, or visually what this looks like, again, I've done this before, I just want to go over it again just for completeness sake, and also because it's really interesting. So if we have x, y, if we have a curve like this, let's say it's from here all the way, let's say we want to look at this segment here, and let's say we're zooming in really closely, and this is a from the distance from here all the way to here. Let's call this dx, so we're really small inside. But then this one from here to here, this is not dy, this is actually from here to here is delta y. That's because this the dy is based on dx, as in the rise over run dy over dx. So that's based on the slope there. And then this total distance across, this is what our delta s is. That's the distance from here all the way to here. So that's our change in arc length. Or I mean, that is the arc length. So that's the arc length from there. But then if we were to draw the ds or dy, those are all dependent on the dx, and that's based on the slope. So if we draw the slope exactly here, what we end up getting is, draw one bit higher, like that. That's at this point, and then this full length is our dy, and then the ds is across like that. So this is what the ds represents. It represents a small, infinitely small segment of our arc length, or the length of the curve, like that. So yeah, that's what it is visually. And then when we apply this stuff here, how this is looked at visually is if we graph this out. Let's say if this is x, that's y. So for this one, if we had a curve like this, some random parametric curve, what this means is if we were to rotate this all the way across the y-axis, the x-axis, like that, and let's graph this. This looks something like this. So let's draw it a bit neater, somewhere here, and then this goes down, up, so something like this. And then when you rotate it, you get something like that, where this distance across here, this is our y. And then when we rotate this one segment, what we end up having is a circle like that, and dashed line across here, where the circumference of this, draw us a better line like that, where the circumference is c, or circumference, circumference like that, equals to, well, that's just 2 pi and then y. That's just the radius is y. So that's how it is visually. And then the ds, the ds over here can be considered as a infinitely small, the thickness. So that could be our ds across, which is this is a zooming in of this. Yeah, so we can kind of see like this whole giant thing could be like a zooming in of this inside this piece there, and that's what the ds represents. I'll draw it like that. So that's like a zooming in. So yeah, that's how it is visually. But then likewise, we can also graph on the other type of rotating about the y-axis. So if this is the y, this is the x. Let's say we had a curve like this, etc., and then we rotate about the y-axis like that. We get a shape that looks something like this. Whoops, let's see how this is. This is going to be like this, and then like that. Yeah, so something like this. And then rotate this across, and rotate it across like that. We get a shape like that, and then what we have here is, instead of the radius y, we have radius x, like that. And then likewise, we could rotate across here, and then we'll have a radius, or a circumference like that. I'll draw a better one, dash dash. Alright, so we have something like that, and then this is now our circumference is going to be c is equal to 2 pi, and then the radius x. So that's how it is visually, and then again it has a infinitely small ds, which corresponds to that all the way above, etc. So yeah, that's how it is, and this is a good way of memorizing it. All we do is look at a parametric curve. We just look at the circumference, and when we rotate it across, in this case, this would be just 2 pi x, and then the total thickness is ds, and then we would take the integral to sum it up to the full surface area. And then the ds symbolically looks like this, where the ds formula is just going to be dx squared or plus dy squared, all square root. And in parametric form, we do it like this: a derivative dx over dt squared plus dy over dt squared times a dt at the end, but we square root before. So anyways, that's all for today. Hopefully you'll learn from this pretty interesting video on surface area, and I just wanted to clarify a bunch of stuff on this one here in part 3, so that's why I did this video separately. Anyways, thanks for watching. Hopefully you learned. Like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.